Okay, let's start. We would start with continue with recursion. In last class, we have taken the example of computing a square using recursion. We discussed about 4 approaches. That was to give you general idea about how recursion works. Now we look at some more examples which are part of a course, which is mentioned specifically in syllabus, and we look at how do we solve those problems or write programs to get the answers using recursion. So just on a theory side, where does recursion used? And you can probably see it reflects in nature, it reflects in all part of our life, though we study it formally in computer science, but it is there in bioinformatics. You look at a tree has a stem, there are branches. So tree is kind of a recursive structure. Mathematics, we see recursion, number series, nature examples, the rivers, river get into sub-rivers, get into the rivulets, and we same kind of continues. We all know about Chinese dolls, one bigger doll containing similar doll inside. You open it to get another doll inside. Some people call it Japanese doll, Chinese doll, all our own wooden dolls. And any art pattern you take inside the same square, inside a square, something of that kind, spiral inside a spiral, or you take even flowers, with the same petals coming from the same. So we have recursions occurring in nature a number of times. So when you study recursion in computer science, it will help us developing a simple solution, a succinct, easy to understand look solution, very simple program. Though we have to be a little careful how do we write that program. So fundamentally, if you look at recursion, all we do is, given the current problem, find a similar smaller problem, find further smaller problem, keep finding to a smallest problem, which we can solve by some means, by manually, by whatever logic. And once we solve the smallest problem, we use the solution of that problem to build upon the solution of the bigger problem. And that's how precisely the recursion works. So you can look at recursion as defining a concept using the definition itself. Use the same definition to smaller problem, and that's how we look at, and we all know Fibonacci numbers. A third Fibonacci number is defined in terms of 2 previous Fibonacci numbers. And we look at those, how things will grow up, look at all the answers. Recursion can be defined or invoked in 2 ways, called direct recursion or indirect recursion. So if I am solving a problem using a similar, smaller problem, like assuming I need to draw a big rectangle and I fill a big rectangle, and that I do that with a smaller rectangle, further smaller, and so on and so forth, then build upon those, that is direct recursion. If I solve the problem using, let's say, something else, and then come back to the square, so a rectangle may call a circle, or ellipse may call back as rectangle again, and keep going till we get a smaller, and that is indirect recursion. So both means are available. Finally, we solve a smaller problem. Using that solution, we build a solution, a bigger problem, and that's how basically the recursion works. So we'll take few examples today. One is sum of numbers 1 to n. We probably all know that sum of 1 to n is n into n plus 1 by 2. But we will look at how do we solve it using recursion, and how do we solve it using non-recursion, and what are the different ways of solving it using recursion. Then we also look at GCD, called greatest common divisor or highest common factor computation. We look at how we can use recursion to solve that problem. And we also look at factorial and how do we solve. And next class, we probably look at Fibonacci numbers and continue from that perspective. So let's say our problem is given n numbers 1 to n, we need to find sum of first positive n numbers. That is 1 plus 2 plus 3 plus 4 plus 5 up to n. So graphically, if you want to look at, you can say that this is 1. This 1, 2, 3 squares, 4 squares, 5 squares, 6 squares, 7 squares, and so on and so forth. So if you can count the number of squares, we are basically finding sum of 1 plus 2 plus 3 plus 4 up to 7 or 8. So if we build a step arrangements like this, we count number of unit squares, we would get a sum of numbers 1 to n. The non-recursive approach could be simpler. One is we can count it. 1 plus 2 plus 3, 3 plus 3 is 6, 6 plus 4 is 10, 10 plus 5 is 15, and we can do so many additions. Alternately, you look at this shape, reverse it. Let's say we call this as sum of Sn, sum of n number. Take this shape, reverse it, and juxtapose on this side. So if we look at juxtaposing the same figure, it basically makes a rectangle whose height is n. And what is the length of this rectangle? Anybody? Height of this rectangle is n. What would be length of this rectangle? Anyone? Aslam?
Yeah, sir.
Yeah, what is the length of this rectangle in terms of number of units?
It's the same, right?
N by 2, sir.
How n by 2? Can you count the number of? If my width is
n plus 1.
If the height is n, then the length is n plus 1. Because I am putting length plus 1 square here. So n plus 1 is n minus 1, 2. So length is n plus 1, height is n. So what would be the, and look at this rectangle represents Sn plus Sn. That means this rectangle represents sum 2 times. Now given the height n, given the length n plus 1, can you please keep your mic in quiet if you're not speaking? Length is n plus 1, height is n. What is the area of this rectangle? Sama? The height is n, length is n plus 1. What is the area of this rectangle?
n into n plus 1.
N into n plus 1, and this represents sum 2 times. This is one Sn, this another Sn. So this gives me 2 of Sn is equal to n into n plus 1, and that means my Sn is n into n plus 1 by 2, and this is what we know. This is what I call is a non-recursive approach. To understand the area of this rectangle or this stepwise arrangement or sum of numbers 1 to n is n into n plus 1 by 2. Now let us look at how do we solve using recursion. So take the same number, the Sn. Sn represents the sum of number 1 to n. Let's look at a smaller problem. If this is my Sn, and if I remove my last line, then this shape will represent some S of n minus 1. If I take the smaller problem, this figure represents the larger problem of finding sum of n numbers. Then if I remove the last row, this represents sum of number 1 to n minus 1. So if I can solve this, that means if I can find Sn minus 1, all I need to do is add this n into it. And if I add n to this Sn plus 1, I will get my answer. So I can write as Sn is equal to solving a smaller problem Sn minus 1 plus the n, because I know the last two is n squares, and this gives me my answer. And what is my smallest case? The smallest case is n is equal to 1. The smallest case, I cannot do less than that. So if n is equal to 1, we know S1 is 1. For anything else, we can keep finding a smaller problem, add n to it, and that gives me the answer. If we look at a recursive program, how does it look like? Let's say call some Sn, which is sum of int n numbers. Then we say if n is equal to 1, we return 1. Else, what should we return? If n is 1, we're returning 1. If n is not 1, that means n is greater than 1, then what is that we should be returning here? Amrita, Ananya Goda, Ananya Pramod, Anusri. Guys, you have to speak when I'm taking your name, you have to speak.
Yes, sir.
Yes. What would be the answer here when n is not equal to 1? What would my answer be here? What is my smaller problem?
Sir, I can't see the screen.
Can anybody not share the screen?
Sir, we can see, sir.
Yes, sir, it's visible.
Then you're, yeah, visible. So what would the line be here? What is my smaller problem? Anybody like to say? Apeksha? Add what? Yeah, add, fine, but what? Rohit? Let's give a thought. I'm talking very simple case here. Meghna, Sahana,
n plus sum of n minus 1.
yeah. My smaller problem is I decrease n by 1. So that means if I can solve the problem of sum of n minus 1, I add n to that, and that gives my answer. And this will give me sum of n number. So I can solve this sum of n minus 1 using some recursion. At some point in time, n becomes 1. I return 1. And if you see, this basically gives me answer sum of. This is one case of recursion finding sum. Let's look at another approach that you can run the program whichever way it is. Let's look at another approaches. Now consider the same case. I have a sum of n. Now n could be odd or n could be even. In this case, I take an n is odd, let's say, which is 7. And this number of squares in this figure represent Sn. So I can draw this figure into 4 parts. One part is this, one part is this, one part is this, and one part what you see in green light. So if we look at my bigger problem of 7, I've reduced this to 3 smaller problems of size 3 and 1 smaller problem of size 4. So let me repeat. If n is odd, then I reduce this problem to n minus 1 by 2, n minus 1 by 2, n minus 1 by 2, and n plus 1 by 2. So if I can find the sum of 3 smaller problem of n minus 1 by 2 and a solution of another smaller problem n plus 1 by 2, and I add them, I would get my answer of Sn. So I can write this as Sn is equal to 3 times n minus 1 by 2 plus 1 time n plus 1 by 2. This is when n is odd. The same thing holds true when n is even. Let's look at that part. If we look at n is even, this is n is even, n is 8. So again, you look at, we're divided into 3 subproblems of 4, 4, 4, and 3. That means if n is even, I divided my problem into 3 subproblems of n by 2 and 1 problem of n by 2 minus 1. So if I can solve 3 subproblems of n by 2 and 1 subproblem of n by 2 minus 1, I can find the answer. So Sn would be 3Sn by 2 plus S of n by 2 minus 1. Now number can either be odd or even, no other case. Now we know that the smallest case would be n is equal to 1. My answer is 1. The smallest even number is 2. If n is 2, what is my sum equal to? If n is 2, what will my sum equal to be? Hello? Yeah, repeat please.
3.
3. Because 1 plus 2, I'm doing a sum. I'm not counting what n is. So now I can write my simple relation as Sn is equal to 1 when n is equal to 1. Sn is equal to 3 when n is equal to 2. Sn is equal to 3 of n by 2 plus 1 of n by 2 minus 1 when n is even. And if n is odd, then 3 of S of n minus 1 by 2 plus 1 of n plus 1 by 2. Now given this, how does my program become using recursion? So I have 2 base cases and then these 2 cases. We look at the problem, first we address the base case and then we look at the smaller version of the problem. So approach 2, sum of n, if n is equal to 1, return 1. If n is equal to 2, return 3. Otherwise, check whether odd and even. So if n percentage 2 is equal to 0, that means it is even. And what would my answer be? What should I return? If n is even, is neither 1 nor 2. There are 3 sub-problems, and 3 sub-problems are one problem of n by 2, 3 sub-problem size n by 2, and one problem of n by 2 minus 1. So the 3 problems of size n by 2, one problem size n by 2 minus 1. So what should my answer be here? So if n is even, what should I return?
3 of s
Would
n
like
by
to-
2 plus s n by 2 minus 1.
Yeah, so it would be 3 times sum of n by 2. Sorry, there were double arrows, so ignore those. It should be single n by 2 and n by 2 minus 1. If it is odd, then I should say n minus 1 by 2. So let me correct that. It should be this. One minute, guys. Are we okay with this? Any questions here?
No, sir.
Hello? Yeah. Now let's look at another way of same solving problem. I can look at this problem as two smaller problem of n minus 1 by 2 and one problem of n by 2. So if it is odd and even, we can look at same case. When n is odd, I can say two sub-problems of n minus 1 by 2 and one problem of square of n plus 1 by 2. And if n is even, then life becomes simpler. Two problems of n by 2 and one square of n by 2. I look at it this way, and my base case will still remain the same. So I solve it and do my problem, and problem will basically become 1. If n is 2, answer is 3. If n is even, 2 of Sn by 2 plus n by 2 square. And we looked at the square problem using recursion, using by sum. So we can use our indirect recursion. So this is solving same problem. This is using indirect problem of sum of square, computing a square using sum, and we can find that. And this way we'll be able to find sum of Sn. If we look at the program, my recursive program would be if n is equal to 1, return 1. If n is equal to 2, return 3. Else, if n is even, return 2 times Sn of n by 2 plus 1 square by sum, which we discussed in last class, n by 2 minus 1. Or if n is odd, then we return 2 times n minus 1 by 2 plus 1 times n plus 1 by 2 square, and that will get the solution. So we've taken the computing the sum in different ways of using recursion. We will look at next problem, a different problem, which is, let's call computing GCD, a greatest common divisor. So before, I actually wanted to play this game in the class, but we don't have physical class, and let's see if we can do that here. So I'll write, let's say, two positive numbers on the board. So let's say numbers I'm writing is 24 and other number is 80. I've written these two numbers. Your job is to write any number on the board such that this number is already not present on the board, and it could be difference of any of the two numbers on the board. So let me repeat. Take these two numbers. There have been many numbers on the board. Right now I have two numbers. Then I have more numbers. And keep writing the numbers which is difference of any two numbers on the board. So game between two players, player 1 and player 2. And whichever person cannot write the difference, the person loses. So game is how do you decide whether you like to be player 1 or player 2. So will any one of you would like to play the game, which could be player 1 or player 2? Who would like to play the game in the class? You can do internally yourself. Arjun, would you like to play the game? Arjun is not there, looks like. Chatra,
Yes, sir.
Ekant, you like to play the game?
Sir, can you explain once how to play it?
So game is, I have written these two numbers. Okay.
Yes, sir.
Let's say you are player 1 and I'm player 2. Okay.
Okay.
Job is given these two numbers. There will be many numbers on the board. You find the difference of any two numbers and write
Okay.
that number on the board. As long as the number is not already there on the board, you cannot repeat a number.
Okay,
So first
sir.
time you have two numbers, don't have a choice. There is only one difference. So would you like to play first or would you like to play second?
Sir, probably second because the number 80 is highest, so we might get more results in that.
Okay, let's play that game. Let me play first and you play second. Okay.
Yes, sir.
So difference is only 56. There is no other difference. Now you have three numbers. Can you tell me the difference which I need to write? Difference could be of any two numbers which is not on the board.
Which is not on the board. Okay, sir.
Yeah.
Hmm.
So can you give me the difference?
24.
Difference 24 already there.
Okay, sir. 32.
32. How do you get that? Which is 56 minus
minus
24.
24. Yes, sir.
32, right? Now I'll take 80 minus 32, which is 48. Can you see that, guys?
Okay, got it, sir.
Now, can you write another number?
8, sir.
8. How do you get 8?
56 minus 48.
8. Fair enough. Next, I would write 48 minus 8, which is 40. Now, can you give another number?
72. 72. 80 minus 8.
80 minus 8, 72. Now, let me write my number, which is, let's say, 48 minus 32, which gives me 16. Now, what number would you like to write?
No, 32 is the 56 minus 8.
48 is already there. Are there any numbers available? Or you
72
lose the game?
minus 8, sir. 72
How much
minus
is that?
8.
Which is 64, right?
Yes,
And
sir.
now
60.
I cannot write any other number on the board. All numbers are written.
Yes, sir.
That means I lost the game, you won the game.
Thank you, sir.
Okay, let's look at another number. To play this game, let's say in this case 30, 80, or let me take this number 25 and 55. So let me take the number 25 and 55. Who would like to play the game? Anybody else? Abdullah?
Sir, it is 30, sir.
Ekant? Now, would you like to play the game? First, let's agree. Do you play the game? Who wants to play the game? Just Haris?
Sir?
Yeah, who's speaking?
Sir, Hari Krishna, sir.
Hari Krishna. Okay, Hari Krishna, let's play the game. Okay.
Yes, sir.
You want to play first, or should I play first?
I will play, sir.
You play first, right?
Yes, sir.
Okay, give me the number now.
Sir, show that picture again, sir.
Oh, sorry. Okay, my mistake. Can you see it now?
Yes, sir.
Yeah. Give me the number.
Sir, 30, sir.
30. I write 30. For you, now I will write 55. 30 minus 25 is 5. I written 5. What is the number you like to write?
50?
50. Okay.
Yes, sir.
I'll write 45, which is 50 minus 5. Your next number?
Sir, 35.
How much?
35.
How do you get 35?
30 minus 5, sir. And 25, sir. 25.
25 already there, bhai.
Yes, sir. I lost, I think, sir.
No. Numbers are available.
20 is
Anybody
there,
else?
sir.
How much? Tell me.
20. 25
Yes, sir, 20,
minus
sir.
1.
50.
20. Okay. Now I'll write 15. Next.
10.
10. What is that I can write? Let me think about it. I'll write 35, which is 45 minus 10, which gives me 35.
40.
40. Can I write any more numbers?
20.
20 is already there. I cannot.
That's it, sir.
So how do you decide, given two numbers, whether you should play first or second? Like previous case, when I played first, I lost. In this case, when I played second, I lost. So given two numbers, how do you decide whether to play first or second? Is the game clear?
The odd and even.
What do you mean? So if the numbers are odd, you want to play first, and numbers are even, you want to play second? Is that what you're saying?
Sum of the given
Yes, sir.
numbers, if it is odd, we will win.
Okay, let's say 30 and 80. What do you like to play? You like to play first or second? One is odd and one is, both numbers are even. I'll give you the two
Second, no,
numbers.
sir.
Why? Or take the case 2555, 2560. We saw that in 2560, 2550, first player won. In 2480, sorry, yeah. In 2550, the first player won. In 2480, second player won. Now, how do you decide in 2560, one is odd, one is even? You recollect in this case, what was my smallest number written? 8. When you look at 2555, what was my smallest number?
5.
5. What would be smallest number when you play 30 and 80?
2.
No. How will you get 2?
0.
20, sir.
No, 0 can't be
10,
there.
sir.
10 is the right answer. What about in this case? 25 and 60?
5.
5. Now, can you tell me the correlation? What does this number correspond to when I look at these numbers? What is 8 with respect to 24 and 80? 10 with respect to 30 and 80? 5 with 25 and 55?
We will get
What
8
is the-
numbers.
Hmm?
We
We'll
will
get
get single digit numbers.
No, okay. So let me change the number as, let's say my number is 24 and 120. What is the smallest number you will get? Can you
12.
quickly play and tell me?
12.
No. It will not be 12.
Sir, 5.
Can you try play the game? Why don't you play the game for 2 minutes and tell me what the number would be?
Sir, 5.
Sir,
Just
14.
work out yourself and tell me. Or let's play the game, okay? Let's play the game again.
Sir, it's 4, sir.
Let's play the game, okay? 24, 120. What is the next number? Difference?
86.
No, 96. 120 minus 24 is 96.
Sir, least value is 5, sir.
I'm coming to that now, 96. Is this okay?
Yes, sir. Yes, sir.
What is the next number you can write?
72.
72. What could be the next number you can write?
48.
48. What the next number you can write?
24.
Already there.
26.
14.
14. How do you get 14?
24, sir. 96 minus 70, 96 minus 72 is 14.
No, 90 plus 72 is 24, ma'am. Can anyone tell me what the difference is? Any more number? You cannot write any more number. We already written all possible differences.
Yes, sir. That's it.
So smallest number is 24. Let me put another one. Let's say number is 24 and 90. Can you tell me what the smallest number would be?
24, sir.
Okay, let's play the game. Give me the next number.
66.
66. Next,
42.
42,
42. Next,
48,
how do you get 48?
90 minus 42.
Yes, 48. Next,
18. 42 minus 24.
18. Next,
Sir, 6. 48 minus 42.
48 minus 42 is 6. Next,
So
12.
how much?
12.
12. 18
18
minus
minus
6. 12. Next,
60.
60. 66 minus 6. 60. Next,
30.
30. How do you get 30?
Sir,
48
36,
minus
sir.
18.
48 minus
36,
18.
36.
48 minus 18, or how do you get otherwise?
Sir, 36.
36. How do you get 36?
42 minus 6.
42 minus 6 is 36. Next,
65.
65. How?
No,
54.
54. How? Tell me how.
66 minus
Sir,
12.
So 54. Yes.
Sorry.
Next,
84.
84. Any more?
78.
78. Are you left with anything? You will have
70.
one more number.
72.
72 is not there. Yes. Return all that. So my smallest number is 6. Now can you tell me, when I took 24 and 90, my smallest number was 6. When I took 24 and 120, my smallest number was 24. What is the correlation?
The greatest factor of the two numbers.
Yes, it is the greatest common divisor. So if we keep playing the difference, you cannot write a number which is smaller than greatest common divisor. And if you look at all the numbers, these numbers are multiple of greatest common divisor. All these numbers are multiple of 6. There is no number which is not a multiple of 6. Similarly, when we wrote 24 and 120, we ended up writing 24, 48, 72, 96. And we have 120. Again, these each are multiple of 24. So all the differences you write are multiple of greatest common divisor. Now, how do you decide whether you are the first player or the second player? All you need to do is look at, when you look at the number 24 and 90, total how many numbers I wrote? Other than these two, total how many numbers I wrote?
13.
13. In this case, how many I wrote? 3. Because this was already there, I ended up writing only 3. So if you look at, if you take the smallest number, divide the largest number by the smallest number, which is 15 in this case, which is an odd number. If you take a GCD, using this number, divide into the largest number, if the answer is odd, first player would win. If this answer is even, second player would win. So if we look at the case, in this case, 24 and 80, greatest common divisor is 8. Largest number is 80. So 80 divided by 8 is 10, which is an even number. Second player wins. 30 and 80, GCD is 10. 80 by 10 is 8. Again, even number. That means second player would win. 25 by 55, GCD is 5. 55 by 5 is 11, which is an odd number. That means first player would win. And next case, 25 by 60, again, it is 5. 60 by 5 is 12, which is an even number. That means second player is win. So the GCD, so using GCD, you can play a very interesting game of with the kids, with other children to decide how do you win. When you look at the logic, you decide. So just wanted to build the interest of how do we compute GCD, what GCD importance is. So GCD can be used to play the game. It could become an interesting game. Now, what you want to do is, how do you compute GCD using recursion? So we'll look at Euclid's algorithm, which is basically, you can keep finding the differences, and then once you cannot find the differences, you'll get that answer. So basically, GCD of A comma B is B by Euclid algorithm. If A is equal to 0, answer is B. Otherwise, if A is greater than B, you call GCD B comma A. Basically means always call first number is smaller than the second number. And when first number is 0, answer is the second number. And if A is already less than B, then call GCD with A comma B minus A. So keep calling recursively. Some point in time, B minus A would become less than A, so you call BA. When you keep calling, at some point both would become the same, the difference would become 0, and then I will get the answer as B. And this is basically GCD algorithm. So if you look at algo would be if A is equal to 0, return B, else if A is greater than B, invoke GCD B comma A, else invoke GCD A comma B minus A. And that would give you GCD of two numbers. So I recommend you to work out the exercise, run the program yourself. Programs are uploaded, play with it, and see can you do that. So I'm done with the class today. We are out of time. Close the time. So any questions, let me know. Otherwise, I'll stop here.